In this video, we're going to talk about matrices and systems of equations. And specifically what we're going to be doing is using the inverse matrix to solve systems quickly. So just a little flashback to something that we said in section 16.2 before we get underway here. If someone gives us a system of equations, such as this one, there is a fast way to write that symbolically. So symbolically, we would write this as ax equal b, where a is the coefficient matrix for the system. X is a matrix that contains our variables. And we usually write those variables just in the form of a single column. And then the capital B here represents the constants from the system. And again, we write those in the form of a column. So if we take this highlighted system here, and we actually write that in this shorthand form, we sometimes call that a matrix equation. What that would look like is, here's your coefficients. So we're just pulling the coefficients out of the system, putting them in the same position as they were in the system, so 2, 3, 3, 5. Beside that, we write a column of variables, and then we say that's equal to a column of the constants from our system. So just pulling out the constants -4 and -5. So let's think of it this way. This is the long way of writing down a system of equations, and this is the short way of writing down a system of equations. And then just so that our terminology is clear, we'll call this short way a matrix equation. So the idea of what we're going to do in this section is we're going to turn a system of equations into a matrix equation, and then we'll see that by using A inverse, there's a really fast way to solve this system. So let's call this part of the discussion, let's call that notation. And now that we've had a refresher on that notation, we can see our main idea. So the fact says a system of equations has solution x equal A inverse times B if A inverse exists. So I'm going to put a star beside that. So the idea is that we've written our system of equations in that shorthand matrix form, ax equal b. And once you've got it written in that form, then you can solve it by saying x equal A inverse times b. That will work whenever A inverse exists. So let's try to understand why that's true, and then we'll jump into an example. So suppose you have a system of equations that looks like ax equal b, and let's say that you know that A inverse exists. So we could multiply both sides of this equation by A inverse. And the whole point of doing that is that A inverse times A gives us the identity matrix. That's by definition of A inverse. So A inverse just comes along and undoes whatever A was doing. So A inverse times A is going to give us the identity matrix. And then we said in section 16.2 that when you take the identity matrix and you multiply it by any matrix, you just get that original matrix. So you get x equal A inverse B. So the reason why we care about this is because if we think about what x is, it's a matrix that contains our variables. So it's just a little matrix like xy, and it's this is giving us xy equals, some number, some number. So it's just popping out the solution to the system. All right, so what's the main takeaway from our fact then? Really, it's just this equation. I might highlight it here. Just this equation, x equal A inverse times B. So we're going to do 3 examples in this video, and they're all going to have the same format. The problem is just going to ask us to solve a certain system by finding A inverse. So the way the process would work is we would need to pick out what A is. So A just represents the coefficients for your system in the same order in which they were written. So 7, -3, 2, 1. Okay, then we're going to find the inverse of that matrix. So let's just recall on the side the formula for the inverse of a 2 by 2 matrix. So if A looks like A, B, C, D, then A inverse looks like this. We're going to go 1 over the determinant of A being AD minus BC. So we're going to go 1 over that determinant. We're going to swap the diagonal entries. So the D and the A change position, and then the off diagonal entries just get their signs changed. So that goes back to our previous video on finding the inverse of a 2 by 2 matrix. All right, so with that formula in mind, first thing I would do is just calculate this determinant of A. So we go 7 times 1 minus the product of the backwards diagonal. So negative 3 times 2. So 7 plus 6 gives us 13. Okay, and then once we have that number, then we can write down A inverse. Say A inverse is going to be 1 over 13 times the following matrix. The 1 and the 7 change position, and the off-diagonal entries just get their signs changed. So now that we've got A inverse, we're going to use that key formula that we just talked about, which says that X equals A inverse times B. X is a column matrix that contains your variables. So we're going to say the matrix XY is equal to this matrix A inverse that we just calculated times B. And so we have to just refresh our memory on our notation. B represents the constants for the system. So if you look back at the original problem, what were the constants? 25 and 9. So B is just a single column that contains those constants. All right, so to solve the system, we're going to do just one step of matrix multiplication, and then we'll have our solution. So for our matrix multiplication, let's circle the rows of the first matrix and circle any columns in the second matrix, and we're just going to do some dot products here. So we'll have matrix XY is equal to 1 over 13 times the following 2 by 1 matrix. Well, we're going to do our dot product. 1 times 25 plus 3 times 9 gives us 52. And then negative 2 times 25 plus 7 times 9 gives us 13. Okay, and then once you've got this 1 over 13 out in front, you can think about just multiplying through. Each of these numbers in the matrix divides nicely by 13, so we get a really nice answer here. Matrix XY is equal to matrix 4, 1. And so that's just alternative notation for saying XY equals 4, 1. If you wanted to confirm that you've got the right answer, then you could take these X and Y values and we could just scroll back to the original system and confirm that, yep, that satisfies the first equation, and yes, it satisfies the second equation as well. So we're sure that we have really found a solution to the system. So if the problem says solve by finding A inverse, then really what it comes down to is doing your calculation for A inverse and then breaking out this formula that X equals A inverse times B. And that gives you a quick way of solving your system. So again, we're going to solve the system by finding A inverse. So I would first write down what our matrix A is just by pulling the coefficients out of the system of equations. There we go. 2, 3, 3, 5. And then we can think about finding A inverse. So to find A inverse for a 2 by 2 matrix, we're first going to calculate the determinant of A. So we multiply the entries on the main diagonal, and then we subtract off the product from the backwards diagonal. So 2 times 5 minus 3 times 3 would give us 1. Okay, that's nice. Our determinant comes out to 1. And then we can write down our formula for A inverse. So A inverse is going to be 1 over this determinant times the following matrix. We swap the entries on the main diagonal and we change the sign of the entries on the off diagonal. And since this number out in front of our matrix is just 1, I'm going to erase that. All right, so there's our inverse matrix. Then we break out our key formula for this section, which is that X equals A inverse times B. And then we just need to remember the notation of what X and B represent. So X is just a single column that contains our variables. I'm going to write down our matrix A inverse. And then B is just a single column that contains your constants from the original system. So let's scroll back up here. Look at the constants on the right side of the system, -4 and -5. All right, so that's what we'll plug in there. And then we'll do a little matrix multiplication, and that's going to give us our answer. So we're going to have our answer in the next step. So doing our matrix multiplication, let's circle the rows of the first matrix and any columns of the second matrix, and we're going to do some dot products. So 5 times -4 plus -3 times -5. That's going to give us -5. And then second dot product, we're doing -3 times -4 plus 2 times -5. Okay, so that gives us 2. Therefore, we've got our solution to the system, x equals -5 and y equals 2. So you could write xy equals -5, 2, if you like, means exactly the same thing. And with that, we're going to try one more example of using A inverse to solve a system. So let's solve the following system by finding A inverse. So first thing we could do is just write down what our matrix A is. So A just contains all the coefficients of the system in the same order as they're written. So 1, 2, 2, 1, 1, 1, and then in the bottom row, notice that there are no y's in that bottom equation. So you just write 1, 0, -2. Okay, now let's think back to our previous video. We saw how to find the inverse of a matrix. We said for a 2 by 2 matrix, you're just going to use the formula. But for 3 by 3 and bigger matrices, we have to use that Gauss-Jordan method, or that's just a fancy way of saying we have to use row operations to find the inverse. So what we're going to do is we're going to put our matrix A into this matrix, and beside that, we're going to write down the identity matrix. So let's just reorganize this a little bit. We'll write down our matrix A. Beside that, write down the identity matrix, which has got 1s along the main diagonal and 0s everywhere else. And we're going to do some row operations, and we're going to turn this left side into the identity matrix. And as we do that, what's going to come out on the right side is A inverse. So that's the plan for finding A inverse. Right, so the procedure is that you want to get a 1 in the upper left-hand corner. That's already done for us. So we want to get 0s in the rest of column 1. That means we want to get rid of these 2 1s here that are sitting underneath our pivot. And the correct operation to do for that is to take our current row plus or minus some number times our pivot row. So for example, for the 1 that's sitting in row 2, you want to go row 2 minus row 1. As for which number you're going to use, it's just the negative of whatever number you're trying to eliminate. So if you're trying to eliminate a positive 1, you use -1 times your pivot row. In a similar way, we would go row 3 minus row 1 to get rid of that 1 that we see in the bottom left-hand corner. So top row will stay the same, no changes there. So let's try row 2 minus row 1. We're going to have 0, -1, -1, -1, 1, 0. And then row 3 minus row 1, we're going to have 0, -2, -4, -1, 0, 1. So that way our first column is now entirely cleaned up and we're ready to work on column 2. So from our previous pivot, we're going to move down and to the right, and we want our new pivot to be in this position. So we're going to get a 1, which we're calling the pivot, in that central position in our matrix. The way we're going to get a 1 is just divide our row by an appropriate number. So we're going to go row 2 divided by -1, and that's just going to cause a sign change all across that middle row of our matrix. So 0, 1, 1, 1, -1, 0, and we'll just recopy the top and bottom rows. So I'll circle that 1 and we'll use it now to get 0s in the rest of column 2. So what we're trying to do now is get rid of the 2 and the -2 that we're seeing in column 2. The correct operations would be row 1 minus 2 row 2 and row 3 plus 2 row 2. For our top row, if we go row 1 minus 2 row 2, 1, 0, 0, -1, +2, 0. Middle row is not changing, so I'll just recopy that. And then for the bottom row, row 3 plus 2 row 2. Okay, so 0, 0, -2, 1, -2, 1. So we're in the home stretch now. We just got 2 more operations to go. What we need to do here is just clean up that third column. So we're going to get a 1. Let's do that just by dividing row 3 by -2. So that's going to give us 0, 0, 1. Continuing to divide by -2, we're going to have -1/2, +1, and -1/2. And our top 2 rows can just get recopied. Good, so very last step, we just need to get 0s in the rest of column 3. So we need to get rid of this 1 that's just sitting above our pivot. So let's think about the correct operation there. We would want to do row 2 minus row 3, because the pattern is take your current row and then go plus or minus some number times your pivot row. Well, our pivot row is row 3 and our current row is row 2. And it's a positive one that we're trying to eliminate, so our number here is going to be a negative 1. So row 2 minus row 3, we'll get that done. Row 2 minus row 3, 0, 1, 0. We'd have 1 minus a half. We'd have 1 minus a negative half. So that's 1 plus a half. Let's call that 3 halves. Continuing to work our way across, minus 1 minus another 1 gives us a negative 2. And then 0 minus a negative half is going to give us a positive half for that middle row. And then top and bottom rows can be recopied. So we've now succeeded in getting the identity matrix on the left. We've just got 1s along the main diagonal and 0s everywhere else. So that tells us that this matrix sitting on the right side must be A inverse. So I'm just going to circle this. So let's just scroll back to the original problem for a moment and we'll just see where we're at. So here was the original problem. We wanted to solve the system by finding A inverse. Okay, so we found A inverse. The last little piece of the problem is going to be to use that formula x equal A inverse times B. And to do that, we're going to need to know what the constants for our system are. So let's just store these constants away in our memory. 17, 9, negative 9. All right, so we'll come back to where we were. And to finish off the problem, we'll say now x equals A inverse times B. X just represents the different variables in the system written in the form of a single column. We're going to take our inverse matrix and we're going to multiply that by B. B just represents the constants from the original system written in terms of a column. So 17, 9, and negative 9. So very last step then is just to do a matrix multiplication to get this figured out. So we're going to circle the rows of our first matrix, circle any columns in our second matrix, and we're going to perform some dot products. So we're going to end up with 3 numbers, and these are going to give us the values of x, y, and z. Right, so for our first dot product, we're going to go minus 17 plus 18 is 1. For the second dot product, I might write down what I'm doing. 3 halves times 17 minus 2 times 9 plus a half times negative 9. Well, this sounds like I'm going to type that into the calculator. That gives us 3. And then finally for our last dot product, I think I'll write down again what we would type into the calculator. Minus a half times 17 plus 1 times 9 and then plus minus a half times negative 9. That gives us 5. So in other words, the solution to the system, if you prefer to write it as an ordered triple, x, y, z equals 1, 3, 5. So we found A inverse using row operations, and then we use this key formula, x equal A inverse times B, to solve the system. So that's our video on using the inverse matrix to solve systems. Thanks for watching.